What's up people, and welcome to my tutorial in Pragmatic Data Science. So in the coming tutorials we're going to take a look at something called similarity measurements. We're going to take a look at why we need them and different kinds of similarities that you can do depending on how your data looks and why you would also want to do this. So the first thing we're going to start taking a look at is what the actual problem is and why this is a non-trivial problem to solve. So you can imagine a scenario where you have data that looks like the data that we have previously been working on in this tutorial series. And I've copy-pasted from the CSV file from the weather data from the Git repository. So the data is separated by semicolon here. And you can think of these as vectors. Each row is a vector. And each column in that vector is the index of that column can be thought of as a dimension, where most of these columns are not comparable to each other. So you cannot say, for example, the first column here is the date, and the second one here is the Fahrenheit temperature. And of course, you cannot compare these to each other and see if a date is similar to a temperature, because these are different dimensions and they are not comparable. And this is what makes it problematic, because if you want to answer questions such as if there is any other day that has similar weather than today, if you want to answer questions if there was what the sale rate of that day was, and in order to make a prediction for today's sales, right? And also you want to be able to answer questions if there's any 2 days that had most similar weather to each other, and also if there is like any subset of common weather, so what the most common weather of the data set is. And from this data set we basically cannot compare the dimensions to each other. And if you think of the pathological case that 2 rows actually have identical data, that is trivial to do, because you only need to, parse it to a string and see if they're equals. And that will of course give you the perfect similarity. But this isn't really helpful in terms of implementation, because of course you can find duplicates like this, but many times you would have small variations that they're really similar, but they're not equal. So you also want to be able to get some kind of measurements, like a floating point between, -1 and 1 of how similar they are. Are they dissimilar? Or is there any are they not comparable? Really, is the similarity equal to 0, meaning that they're not disequal, but they're also not equal? Or do you have a 80% similarity, or do you have like a 80% dissimilarity? And this has huge applications, of course, in different scenarios depending on what you're trying to build. And so that's the problem that we're trying to solve, being able to compare this multidimensional data to each other. So the first thing we're going to start taking a look at is something called the Euclidean distance, which is a very common distance to use. And in this data set, in these examples from the similarity measurements, these x and y variables that we use for the functions are always going to be vectors of the same length also. And you can ignore this figure here, this because I copy-pasted it from my thesis. But you can see here how we would iterate over each element of the vectors, and we would take one minus the other one, and then we would square it. And we square it here because we're not interested in, we want to have the absolute values basically. So if this becomes a minus value, you would have a minus value multiplied by another minus value, so that gives you a positive number. And if this is a positive number, yeah, it's still positive. It's going to be positive either or. So this is like taking the absolute value of it, and that is also why we use this square root thingy here. So we compensate for this exponent here that we're taking, right? So you do this for each element, and then basically it just sums up the result of that with this sum here. So you would plus everything together, and that is your Euclidean distance. And it's fairly straightforward, but what can be kind of confusing is why you would use Euclidean distance, and most important, when you cannot use Euclidean distance, because many data set doesn't even exist in the Euclidean space. And what that means is, for example, let's see if I can explain this in a straightforward way, but if you imagine a scenario like this, where you would have 3 points here. You would have this point here, you would have this point here, and you would have this point here. If you imagine this as a map, if I go east like this, and then I go north this distance, I end up in a point here, x22, y22. If I start from the same location and I just go this distance instead, if I go on the diagonal like this, according to this distance here with this grade, where you take the hypotenuse and everything, if I end up in the same place here, it exists in the Euclidean distance. This is the Euclidean distance, and the data exist in the Euclidean space. So in the Euclidean space, there exists the notion also of average between two values. And you can think of there is an absolute location in the space, meaning that they're transitive in the way that I explained previously, that you can go from one space to another immediately without like doing this and this. And in the non-Euclidean space, each point has, it's the Euclidean distance in the non-Euclidean distance is based on properties of these different points, but there is no concept whatsoever of location in that space. So if we take a look at, we backtrack here to our data and take a look at this, you can see that we have these yes and no variables here, whether it was raining or not. And you can see how these variable does not exist in the Euclidean space, because you cannot take a plot like we previously had and say that here is where it's raining, and if you go east and up, you end up in the some other space where it's now foggy as well. It doesn't make sense to compare them like that. But you can do that with, and also you cannot take an average of whether it was raining or not. That also doesn't make sense. But if you think of the dates instead, and you can compare them, saying that, if I take these two dates here, there's actually an average of them, like the day just between them, right? And the same thing goes for the temperatures here. There's also a notion of an absolute space, in the sense that you can take an average of two temperatures. And the same goes for all of the floating points, I think, in this data set. So I hope I didn't confuse you guys too much with the Euclidean distance here. It can be a bit tricky to understand it, but the calculation of it is fairly straightforward, and I hope you understood it right. If there's any uncertainties, just leave it in the comment section and I'll try to explain it further, right? So don't forget to subscribe if you haven't already, and I will see you on the next tutorial. Bye bye.